Alright, so now we're ready for projectile motion part 3. And we're going to deal with problem type 3, which is where we launch at an angle, but delta y does not equal 0. And so there's actually a couple different ways we could do that. We could go up onto a cliff, and we could launch our projectile at some angle above the horizontal, and it would follow a parabolic path up into the air and then back down to the ground. And if this cliff is height h, then delta y at the end would equal negative h. Now another way we could do that is we could go up on top of a cliff again, but this time we could actually launch our projectile at an angle below the horizontal. And then once again it is going to follow a parabolic path. Once again, if our cliff has some height h, delta y at the end is going to equal negative h. But for this part, v naught y is negative. For the first type of problem, v naught y would be positive if we make up positive and down negative. The third option would be that we actually start down on the ground and launch our projectile up on top of a cliff that has some height h. And so if we do that, we would have to, of course, launch it up at an angle above the horizontal. And now our projectile could follow a parabolic path that looked something like this. And if we do that, delta y at the end would actually equal positive h. So all these problems are basically the same type. They're just slight variations. So let's look at an example. Alright, so at the end of class today I asked you guys to try this problem because this is review for you guys. You saw projectile motion last year. So a stone is thrown from a 34.6 meter cliff at a velocity of 13 meters per second, 13 degrees above the horizontal. And I asked you the same three questions we looked at for projectile motion problem type 2. How long is it in the air? How far does it go before it hits the ground? And what is the maximum height? So the only real difference here is this time we're going off of a cliff, and we're going to follow this parabolic motion up and then back down and hit the ground. So if I'm looking at my horizontal components, then I know that Vx is going to equal, in this case, 13 times the cosine of 13. And so we get 12.7 meters per second for our horizontal velocity, and then we will also write in our vertical information. And so our vertical information, v naught y, comes out to 2.92 meters per second. A comes out to negative 10 meters per second squared, and delta y at the end is negative h, so it's negative 34.6 meters. So there's two ways we can go about finding the time that it's in the air. The first way to do that is to say delta y equals v naught y t plus 1/2 a t squared, and go ahead and plug in your values. So negative 34.6 equals 2.92 t, and then that comes out to minus 5t squared once you plug in negative 10 for a. And then we end up with 5t squared minus 2.92t minus 34.6 equals 0. And then for that we would have to use the quadratic equation, negative b plus or minus square root b squared minus 4ac over 2a. And I usually don't do it that way because I don't particularly like the quadratic equation. So let me show you how I usually do it. So usually I just solve for the vy at the end first. And I do that saying v squared equals v naught y squared plus 2a delta y. So v equals the square root of v naught y squared plus 2a delta y. So we plug in, And when I plug in my values, I find out that Vy at the very end should be negative 26.5 meters per second. Then, to solve for time, I can use Vy equals V naught y plus AT. So T equals Vy minus V naught y over A. So negative 26.5 minus 2.92 divided by negative 10, and we get about 2.94 seconds. Now, to figure out how far we go, it's just going to be delta x equals vxt. So I'm going to plug in my horizontal component of my velocity times the 2.94. And for that part, I get 37.3 meters. Alright, then the last thing we were doing is finding the highest point reached. So to find the highest point reached, we're looking for delta y at the apex, and the important thing to remember is that the y component of the velocity at the apex equals 0, and so v squared equals v naught squared plus 2a delta y, but v at the apex is 0, so delta y at the apex is going to equal negative v naught y squared divided by 2a. So we plug in and solve there. So when we plug in our values, I get a delta y at the apex of 0.43 meters. But that's above the cliff, so to get the delta y above the ground, or the y above the ground, we're going to take the delta y at the apex plus the y of the cliff. So we're going to take our 0.43 and we're going to add that to the height of our cliff, which was 34.6 meters, and we will find that the height at the apex is right around 35 meters. Now at this point there may be a couple of you that are annoyed with me because I told you your answer was wrong in class and made you watch this screencast. As it turned out, the problem I had written down on my piece of paper was launched at 23 degrees, but I wrote on the board 13 degrees, so none of your answers were matching the original answers that I had, but congratulations, watching the screencast was good for you anyway. I'll see you in class tomorrow.